Alright everybody, welcome back. This is the second video on section 8.2 for AP Calculus, connecting position, velocity, and acceleration of functions using integrals. We're going to pick up where we left off at the end of video 1 and look at a few more examples. We'll start here with example 3, which comes from the 2018 AP Calculus AB exam free response question number 2. This is a calculator question, so we're going to go ahead and use our calculator to help us along the way with this problem. Alright, let's see the stem. A particle moves along the x-axis with velocity given by v of t equals blah de blah for time 0 to 3.5. The particle is at position x equals -5 at time t equals 0. Part B asked us to find the position of the particle at time 3. So the basic relationship that we're looking at here is the position at time 3 is equal to the position at a known time, which is this position right here, position at time 0, plus the integral from 0 to 3 of the velocity function. And so the way we're going to calculate this position, x of 3 is going to be, x of 3 is going to be equal to x of 0 is -5 plus the integral from 0 to 3 of this velocity function. And since this is a calculator question, I can just go ahead and calculate that value using my calculator. I've got -5 plus the integral of the quantity 10 sine of 0.4 t squared, close that, close the numerator, divided by quantity t squared minus t plus 3. By the way, it's totally fine to use x on your calculator here. I hope you all know that by this point. With respect to t, from 0 to 3. And hopefully I didn't make any data entry errors. Go ahead and let my calculator figure this out. And sometimes it takes a little bit of time. I almost feel like I need hold music right now. There we go. -1.760. And it looks like I typed everything in correctly, so there we go. That's our position at time 3. Alright, part C. Evaluate the integral from 0 to 3.5 of v of t dt, and evaluate the integral from 0 to 3.5 of the absolute value of v of t dt. Interpret the meaning of each integral in the context of the problem. So first I'm going to go ahead and calculate these. And again, this is a calculator active problem, so I can go ahead and just type that into my calculator. Now I already have the integral set up in here, so I'm just going to delete some things off of here. What did I take before? I took the integral from 0 to 3, so now I just need the integral from 0 to 3.5. And I got rid of the initial position. We'll let this calculate. And then I'm going to go ahead and also I'm going to find the integral from 0 to 3.5 of the absolute value of v of t dt. Alright. And we got 2.844. 2.843 is also acceptable here. And now let's also calculate the absolute value of that. You can just go ahead and put an absolute value in there, and then close the absolute value over here on the end. And we'll see. Sometimes it takes a while for this to calculate, so I'm going to go ahead and move on to the interpretations while I'm waiting for my calculator to calculate this value. So, okay, integral from 0 to 3.5. The integral of the velocity gives us the displacement. Okay, is the change in position or displacement of the particle from time t equals 0 to t equals 5. And I don't have any units for distance or time here, so I can't include any units in my interpretation. See if my calculated value's there yet. Here it is, 3.737. And then my interpretation for this, the integral of the absolute value of velocity, that's the integral of the speed. So that's going to be the total distance traveled. Is the total distance traveled by the particle, oops, that was 3.5, I wrote 5, by the particle from time t equals 0 to time t equals 3.5. Again, if we had any units given here, we would need those in our interpretation as well, but we don't have any, so we don't need any. All right, example 4 should be our last example for this lesson. Yep, it sure is. Example 4 comes from the 2010 AP Calculus AB exam, Form B. It's free response question number 4, which means it was a non-calculator question. A squirrel starts at building A at time t equals 0 and travels along a straight horizontal wire connecting to building B. For time 0 to 18, the squirrel's velocity is modeled by the piecewise linear function defined by the graph to the right. Part A. At what times in the interval, if any, does the squirrel change direction? Give a reason for your answer. So the squirrel changes direction whenever the velocity changes sign. So if this is a graph of velocity, which it is, the velocity is positive, 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 positive. Right here, the velocity is 0, and then the velocity is negative. And then the velocity is negative, 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 negative. And then the velocity is positive. So the squirrel changes direction at time t equals 9 and t equals 15 because the velocity changes sign. From positive to negative, or negative to positive at these times. All right, part B. At what time in the interval from 0 to 18 is the squirrel furthest from building A? How far from building A is the squirrel at that time? Okay, so let's talk about candidates that we have for when the squirrel is furthest from the building. The squirrel starts at building A, so this left endpoint is not a possibility for when the squirrel's furthest from the building. We have 2 critical points and another endpoint, so really our only considerations here are at t equals 9, maybe 15, maybe 18. At t equals 9, the squirrel's moved a certain distance from the building, and that's represented by the integral from 0 to 9 of the function. And then from time 9 to time 15, the squirrel had changed directions at time 9. It started moving away from the building. Okay? Or back towards the building, pardon me. And then at 15, it starts moving away from the building again, up until time 18. But notice that the distance, the integral from 9 to 15 is bigger than the integral from 15 to 18, so it moved more back towards the building than it from 9 to 15 than it moved away from the building from 15 to 18, which tells us that the time that the squirrel is furthest from the building is here at time 9. And then, in order to find how far the squirrel is from the building at that time, I'm going to go ahead and take the integral from 0 to 9 of the velocity function, which I'm just going to go ahead and get by taking the area. And this is a trapezoid, so I'm going to have 1/2 times the average of the bases. The bases, this base right here is 9 units. This base right here is 5 units, times the height, which we can tell from these points the height of this trapezoid is 20. And so we end up with 140 as our value. Do we have any distance units? No. So no units needed in our answer. All right, so time 9, and the squirrel is 140 units away from the building at that time. All right, what else do we got? Find the total distance the squirrel travels during the time interval from 0 to 18. So the total distance the squirrel travels is going to be the integral from 0 to 18 of the absolute value of velocity. We already found out that the first part here is 140. So then we need this trapezoid, the trapezoid from 9 to 15. We're going to take 1/2 times the average of the bases. One base is 6, the other base is 4. And the height of that is 10 units. And then we're also going to add this trapezoid out here. 1/2 times the average of the bases. The bases are 3 and 2, and the height is 10. And if we add all these together, we're going to get the total distance traveled by the squirrel. We've got 140 plus, let's see, that's 10 times 10 times 1/2 is 50. And then this is 1/2 times 5 times 10, so that's 25. We add all of those together, and the squirrel travels a total distance of 215. All right, that brings us to the end of this lesson. We'll see you next time for section 8.3, using accumulation functions and definite integrals in applied contexts. Have a great rest of your day, everybody. We'll see you next time. Bye-bye.